Hello, we are group 1 from 3PANR S2. According to our topic, we want to reduce the electromagnetic interference towards our PCB board design. So, by taking into account that the PCB of each electrical device AMI can be reduced for the whole device, so it will increase electromagnetic compatibility for our PCB board design.
Electromagnetic interface in PCB board design. For the first method, shielding. There are many components in a PCB that can radiate EMI. These include power supplies, IC clock and oscillator, all of which can interfere with AC component. One way to limit EMI from noisy DC component or protect AC component that are susceptible is simply to shield them. Shielding will essentially guarantee that no EMI radiating through the air in the enclosure will interfere with the shielded circuit. If you have a multi-layered board, you can also use a ground plane layer as a shield. As we can see here, this is the picture of the shield material. For the shield material, it will reflect all the EM wave and some will be absorbed into the shield material and it will transmit the EM wave. For second method is separation. Keeping AC and DC system, both chip and tracer, far away from each other on the PCB will help ensure there is no crosstalk between the system. If you have enough space on the board to put physical distance between AC and DC system, you can also cut gaps in the ground plane between components that need to be separated. Gaps in the ground plane will force any current flowing through the plane to go around the gaps, which you strategically can help you reroute the current and around sensitive system. As we can see here, for transmission in ideal environment without noise, we can see there is no crosstalk between the the signal, so it will receive clean signal. And the impact of EMI and crosstalk without mitigation and cancellation, it will disturb the signal and we will receive signal with noise. So the next part is power. In every AC or DC PCB, there should be separate power rail for AC and DC component. DC component can draw spikes from their power supply, creating a voltage transient, while your AC component may be able to operate with this voltage transient. They will certainly not operate at the highest capacity. If the voltage transients are too large, they can produce errors in AC component or stop the circuit from working altogether. For the next part is filtering. Filtering circuits and components are best used when you only want a specific frequency or range of frequency to reach the load end of an interconnect. Flip this. Filter can also be used to remove one specific problem frequency from an interconnect. Filtering is best left to the analog or RF designer that should not use filter circuit to try and remove noise from an interconnect carrying digital signal. For RF and analog system, band pass filtering is typically used to pass signal into a receiver and prevent noise. Power system will also make use of filter, primarily on the output stage of the regulator or the input stage where the device is connected to the main power source. In this usage, the filter is applied to try and remove conducted common mode current that switching regulatory topology have a built-in filter from the inductance. If it have too much noise on the output from your regulator stage, we might need to increase the regulated inductance. That's all from me. Thank you.
One of the design rules for high-speed PCB is we keep our tracers short and direct. The longer electrical tracers can act as antenna and pick up electromagnetic interference EMI, which leading to a potential signal degradation or even system failure. To reduce the risk of AMI, designers should keep traces as short as possible and route them away from source of interference. And long traces also are pricier, and longer electrical traces typically require more material and take up more space on a printed circuit board (PCB), leading to a higher cost. This is why designers strive to keep traces as short as possible in order to minimize both cost and risk of electromagnetic interference. Additionally, using more advanced PCB material and manufacturing process can also impact the cost of longer traces. So, one of the ways to shorten the traces is we use a routing optimization, which we using the computer-aided design (SCAD) tool to carefully plan the trace routine to minimize length while still meeting other design requirements. Second, we can use the component placement, which we optimizing component placement to reduce trace lengths, such as placing components close together that need to communicate centrally. And third, we can use the layer utilization, which we making use of multiple layers in the PCB to shorten the trace length by routing signal through internal layers rather than on the surface. That's all. Thank you.